Good morning.
Good morning, Professor.
Good morning.
Good morning, everybody.
Good morning, everybody. Morning, teacher.
Good morning.
Good morning.
Good morning, teacher.
Good morning. Can you hear me?
Yes, clearly.
Can anybody hear me? Oh, good. Thank you. It's disappointing we can't meet in person, but it sounds like the weather will be really bad today. Yeah. Okay. We'll give people another minute to join, and then we might start, I think. Okay, I'm aware of everybody's time, and that being online is harder to listen for a long time than being in person. So we might make a start, and then I'm not sure if there's a good arrangement for having breaks. Perhaps we can just call a break, in a little while, and then spend 10 minutes and then come back onto the call. Okay. So I'm going to share my my screen. And can you see my screen?
Yes.
Okay, good. Perfect. Okay, I'm just going to see if I can get this to be a bigger screen inside this. Oops. All right. I'm not sure about making this full size inside Google Meet. Does anybody know how to do that? No? Okay, so maybe we can just run through the notes as they are here. I'm sorry?
You can push the on your keyboard control and plus, okay, control and plus at the same time. So it could be bigger.
Control N plus.
Yeah.
Noted, professors, there is an arrow at the right, in the right side of your screen in the top. You get this? The arrow.
I'm sorry?
Yes,
This arrow?
the bi-direction arrow in the top. Yes, of the right. Yes, you can put there. Yes, this.
Yeah, I'm trying.
Yes, you can put to this, and the screen is bigger.
Yeah, but it's not coming up. Hang on. That's usually what I do, but oh, hang on. Maybe it's that one. Okay, let me try. F11. Interesting. All right, maybe we can just go with this like it is. Can you see? Oh, can you see my screen?
Yeah.
Yes. Yes.
Yeah, but which is fine, except I can't make it move. I'm sorry, I'm not used to Google Meet. So I've got this little green point now that I can't get rid of.
Yeah, we got two arrows on the front line. The arrows, you see, you can try it. The arrows, two-way arrows.
This arrow?
Yeah, we have two arrows actually, so you can put each of them to try it.
Hang on, I'm just going to do it again and see. I'm sorry, everybody, for watching my ineptitude with this. I'm used to other things, so let's just try.
Yeah, it's fine.
Right, so I want to, do I use the bottom arrows or the top directional arrows? Maybe these ones. And I have this little dot now, and I don't want you dot. I want you to go away.
Miss Carrie, you want the screen to get bigger?
I want to make this so presentation mode for my presentation.
Right, but I think this one is PDF file. Maybe you can just make the page look bigger. So I think what people are saying is you click on the toggle. So there's the bi-directional arrow.
Yeah, this one.
On the
can you see this bigger
right
now?
Corner. It's on the top right
this
corner.
one. This one. No, the top right corner is where I am trying to point. I've got a little green dot. Hang on.
Or maybe just choose the so the top right corner. So there's that arrow of the paper of the PDF page. I think it's
there is, but I've got a green dot instead of a
Oh, okay. So green dots.
hang on, maybe it's stop annotating. Hang on. Okay. Maybe we'll just go with this, and can you all see the screen well enough?
Yes.
Let me see if we can move it along. I don't think I can move it. Ah, how frustrating. I can't seem to move it inside the thing. Let me try again and see.
Ms. Carey, do you have the PowerPoint slides instead of the PDF file?
No, I just have the PDF file for this one.
Okay.
Just going to try again. Let me see if I can move it along any other way.
Professor Mangerson, do you have another PDF printer?
Do you all have the PDF file with you? I don't want to.
Yes.
Yes,
Yeah,
I know,
me
but it's it seems to be it would be very frustrating to not be able to show it while I'm doing this. I don't understand why I can't access it.
So you can't move your pages?
No, I can't move it when I so I go into just let me make sure I can move it in the actual file. All right, let me try one more time. Let's see.
Where's that green dot?
Yeah, I know, it's a little
I think it's highlighter or some sort.
it is, but I think I've turned that off now, so maybe if I just go into a bigger screen. It doesn't seem to have the control inside the document. All right, I think in the interests of time, does anybody have any other suggestions? What I'm not
Maybe
doing?
someone can share the
That's a good
page,
idea.
and then you can control from afar.
Okay, all right, let's do that. I can do that. Can somebody share the PDF file and maybe have control? I don't understand why I can't do it, but if somebody can try.
Anyone volunteers to do that?
I will do this. Wait for me a minute. I will do this. Yeah.
Do you have the screen up, Mian, or not?
So wait for me a minute.
Sure.
Yes.
That's why I always get anxiety whenever I have online classes.
I know. It's always the case, isn't it? So I have PDF, and if I'm doing it through another platform, I just go, I can easily
Something
just
will
make
happen.
a screen, and it's very easy. But, I'm very jealous now that you can do this and I can't do it.
I think you will know how to do it later.
So do you hear? Yeah, can you see the screen? Not yet.
Not yet.
So how about now?
No.
No.
Like we did see your screen like previously, but then
Yeah.
Okay, now we can see it.
And let me check. It's okay? But
No.
not.
Do you think that
Very
it's
strange.
because of the Google Meet rather than our technical issue?
Yeah,
I think
it has.
maybe.
It's happened before.
Has it? All right. So how about we just go through, if you can all pull up your file. Does anybody not have the document?
Yeah, we have them
Okay,
already.
all right. So what I'm going to do is just go through it, and I'm going to say what page I'm on. Okay, so I'm on page 1. Good morning, everybody. So then we'll move to page 2, and to say that what we're going to do in this presentation today is go through a lecture, as we have been talking about, and a tutorial. And what I want to cover on slide 3 is the lecture for 2 hours. I want to talk about, and we'll probably make it shorter because we're online. I want to talk about Bayesian classification. I want to talk about decision trees and neural networks. And in the tutorial then, we'll talk about the implementation of this and some case studies. Now we'll mix up the lecture and the tutorial a little bit because we're online, and I think that it's harder to listen to. There's also 2 other files that we will use in this session. One is there's an extra tutorial file, a PDF file, and one is an R script. And the R script is called Examples Bayesian ML for Machine Learning. So when we get to those, I'll try and share those slides. So now I'm on slide 4, and the learning objectives for today is, after this lecture, we want to understand a Bayesian perspective in machine learning. I'm going to talk a little tiny bit about a different approach instead of Markov chain Monte Carlo, which we've talked about, MCMC. I want to talk about variational Bayes, just as another approximation approach, but which is much faster than MCMC. So after today, and after the whole course actually, to understand about, to be able to be aware of the different computational tools that we use for analysis. So looking at MCMC and variational Bayes. So describing a Bayesian approach for classification trees and neural networks, and then to identify relevant R tools for Bayesian modeling. So now I'm on slide 5, and we're going to start now, and on slide 6 with the linear regression model. So I'm on to slide 7 now. So slide 7 talks about the linear regression model. And what you see here is just the common linear regression model, y equals x beta plus e. or epsilon. And epsilon is normally distributed with mean 0 and variance, covariance matrix, and it's just got sigma squared as the diagonal. So n here is so it's just like sigma squared for the residual. So we could write this model as y equals beta naught plus beta 1 times x1 plus beta 2 times x2, etc., plus beta p times xp plus epsilon. Now, if p is much greater than n, then we talk about this being a high dimensional data set. P is the dimension, the number of explanatory variables, and if that's much greater than the number of observations, then this is high dimensional. So, and in fact, even if P is very large, and even if N is large as well, we still have high dimension. So that means that we have to have good computational methods to be able to analyse these data. And the goal is going to be to estimate the model parameters, the betas, and also the residual variance sigma squared. So we've seen this before in regression. And if y is a continuous variable, we have a regression approach. And if y is discrete, so binary or categorical, we have a classification approach. So we might have a binary outcome, yes, no, true, false, dead, alive, kind of thing. And we might have categories, red, blue, green, or high, medium, low, those sorts of categories. So Bayesian machine learning is an approach for estimating the model parameters theta. Now, sometimes also, we're going to talk about this in a regression model, but also we might be interested just in a case where we're looking at, for example, classification or clustering, where we don't have a response variable, we only have a set of x's, and we'll get to that in a little while. So an example of a continuous y, so I'm on slide 8, we have house price prediction. So y might be the sale price of a house, and our predictors might be many features, such as location, area, room size, materials, images, and so on. Or we might have stock return forecasting. So we have the number of the daily or weekly return, and our predictors here are the lagged financial indicators, technical ratios, macroeconomic variables, and so on. So examples of a binary or category response variable. So I talked about we could have the disease status, you're diseased or healthy, or it could be credit default. So you default or you don't default. And using, in the credits example, using hundreds of financial indicators or transaction records. In fact, we can use machine learning methods even if we don't have hundreds of them, even if we just have, many, it's fine. So a categorical outcome might be a tumour type classification. So tumour A, B, C, D. We might also have tumours, consumer segment prediction. So we're segmenting the market and behavioural predictors. So many ways that we can have these kinds of binary or categorical response variables. So on slide 10, just give a description of what Bayesian machine learning is. So we want to combine the Bayesian inference principles that we've seen, so the Bayesian methods, with machine learning models. So each model parameter now will be assigned a probability distribution, just as we've had before. And it will also be the design, we'll have this prior distribution on that parameter. So then what we want to do, our estimation, is to estimate the posterior distribution, P of theta, given y and x. And that's going to be proportional to P of y given x and theta times P of theta. So now on day 4, you should be all very familiar with this formulation. So we're now looking at trying to get a probability distribution, a posterior distribution for theta given our observed data. And this is really important. Once we've got that posterior distribution, then we can make all sorts of inferences on the basis of that, the posterior mean, credible intervals, comparisons across parameters, and so on. And our parameters here, we're thinking of that as being the parameters of the regression equation. But it could also be the theta could include missing values, because we can estimate missing values in the same way. We think about giving them a prior distribution, and then we get a posterior distribution for the missing data. A very nice way of being able to estimate missing data. We can also think about theta, our unknown, as being the model itself. So as we saw the other day, we can compare models, the probability of one model, the probability of another model. And so theta, in this case here, we're talking about parameters of a regression equation, but we can also include missing data and even the model itself. So we get from this then uncertainty quantification, interpretation, and also regularization. In other words, the coherence of the model and the output. So we might talk again, just to remind ourselves on slide 11, about the frequentist versus the Bayesian approach. So in a frequentist approach, we think about the parameters as being fixed, and the data's random. So we have some data that's random, and we talk about if we generated other data sets looking like those data, then we could be estimating. We estimate the parameters are fixed and the data's random. In a Bayesian framework, we give conditional on the data. So we're conditioning on the data that we've observed. So the data's fixed, and we think about these parameters as being the unknown. So they're not random in the fact that they can be anything. They have an underlying true value. It's just we don't know what that value is. And so we're trying to estimate that parameter. So we have a likelihood, a prior, and a posterior in our Bayesian approach. So if we go to slide 12, some key differences between the frequentist and the Bayesian approach. Just 4 differences I want to talk about. One is how we interpret probability. So the frequentist approach talks about this observed frequency of events. A Bayesian approach talks about probability in terms of a belief about what that number should be, what that value should be, and then we update that by evidence. And as we get more and more evidence, then we learn more and more about that probability value. The parameters themselves, in a frequentist context, they're considered to be fixed constants and the data's random. In a Bayesian framework, the parameters are random variables, they have prior distributions, and then when we add the data, they have a posterior distribution. So they have a probability distribution around them. We can also think about how we quantify uncertainty. In a frequentist context, we talk about confidence intervals. So this is about the sampling variability. If we took many samples of the same kind as we've observed, then 95% of those samples, if we estimated a confidence interval for each of those samples, then 95% of those intervals would include the true value of theta. In a Bayesian framework, we have a posterior probability and we have that distribution. We build an interval based on that distribution, and we talk about that as being a credible interval directly from P of theta given Y. And for computation is also different. In the frequentist sense, we use analytic or closed form methods. Typically, we can use expectation maximization as an approach in a frequentist method, but typically it will be analytic and closed form. So the types of models that we can deal with are a much smaller family. In a Bayesian framework, we use mainly simulation-based approaches. Some simple problems as we saw on day 1, we can do analytically. Okay. Use some sort of simulation-based approach. So Bayesian methods offer richer uncertainty quantification. Frequentist methods are often simpler and often computationally cheaper, but we can't do more complex modelling and we don't get as much inference from them. Right, let's talk about Bayesian approaches. So I want to talk about Markov chain Monte Carlo, and you've seen some examples of this. I talked about in the days 1 to 3, or days 1 and 2, sampling-based methods, Gibbs sampling, Nicholas Hastings, and we approximate the posterior distribution through this sampling approach. Now, variational Bayes is an approach that says we're going to approximate the posterior distribution. And we do that in a very specific way that enables us to get a good estimate of the posterior distribution through this approximation approach. So this is much faster than doing the full MCMC approach. There are other kinds of approximate Bayesian approaches, Laplace approximation, expectation propagation. I won't talk about those, but if you are interested, then there's a lot of literature on those, and I'm happy to provide some. So examples of Bayesian models are regression, classification, hierarchical models, mixture models. You've seen all of those in days 1 and 2, and also neural network models, and we'll cover those a little bit. So MCMC, I'm on slide 15 now. MCMC versus variational Bayes. MCMC is a sampling-based approach. We generate samples from the posterior distribution, and if we run the sample for long enough, we're going to get an exact replication of that posterior distribution. But we have to do the simulation, so it's computationally expensive. It's good for lower dimensional data sets, not so good for high dimensional data sets because we have many parameters to estimate. So examples are Gibbs sampling, Metropolis Hastings. If we look at an approximation approach like variational Bayes, this is based on optimization. So it approximates the posterior with a simpler distribution. If I have quite a complex posterior distribution, I think about a simpler distribution that has the key characteristics of that complex distribution. So this then is fast, but it's scalable. It can grow in complexity, but it's approximate. So it's good for high dimensional data sets. And an example of this is mean field variational inference. So MCMC is good for accuracy. Variational Bayes is good for speed. MCMC depends on sampling from the posterior distribution. Variational Bayes depends on optimization through a simpler distribution, and we estimate from that. So now on slides 16 and 17 give some examples of 17 and 18, give the actual mathematics of the approaches for Metropolis Hastings and variational Bayes. I'm not going to go through those in detail here, and especially because we're online, but I will leave you to read those, and if you're interested, then to follow up. But on slide 19 now, I'm going to go to slide 19. Are you still with me? Yep. Okay. On slide, hang on, I'm looking at my slides so I can't see you guys. Are you okay? Oh, we've got the slides up. Who's got the slides running? Man. You do?
Yes.
Oh, perfect.
Okay, I'm running the slides for you.
Oh, perfect. Thank you so much. I was looking at my slides. I didn't realize you could see them with me. Perfect. Thank you. Okay, so the key points now is that our mean field variational Bayes, okay, it simplifies the computation, and it's scalable to large data sets. It's fast, but it can underestimate uncertainty when the posterior is multimodal. So it's important for you to understand this. If you may do this coding yourself, it may be part of the packages that you use, but if you read somewhere, for example, in a paper that they're using variational Bayes as a computational method, then you'll understand that this is an approximation method. Okay, if we go to the next slide, to slide 20, this is an example of mean field variational Bayes. So just in our first lecture and in the second one, day 1 and day 2, we talked about this example of a bivariate normal distribution. So we have Y1 and Y2, and they're linked, okay? And we want to and they come from a normal distribution with a mean of some mean that we don't know, and some variance-covariance matrix. And the correlation between the two variables is 0.8, okay? So we have this bivariate distribution. This is like, if it's a normal, it's going to be like a hill, okay? Very nicely, but it's not going to be a symmetric hill because there's a correlation. So it's more like a ridge. What's the word for ridge in Vietnamese? You know, if you have like a hill, but it's got a direction. What's it called?
So that's being bridge, right? Bridge.
Yeah. You know, you climb up onto a mountain, but it's actually got a direction in it. It's not exactly symmetric. What do you call this? Do you know what I mean?
So you mean that is a cardboard, right? Cardboard is linked between the two hill, for example, or two mountain. This is what you mean?
I'll put this in the chat and see if this makes any sense to you. Are you there?
Like sườn núi. What's that?
Let me see. Yeah. This? Sườn núi?
Yeah.
Okay. All right. So that's what we're sort of looking for, okay, in this example. So now, so we have this correlation between the two variables. So if we are using MCMC, then as we saw on days 1 and 2, we will estimate or simulate from θ1 given its distribution, which is just a single normal distribution. So θ1 given θ2 and D, in this case, the data. And then we would simulate θ2 given θ1 and D. And then we would simulate θ1 given the value of θ2 that we've just simulated and D. And that would just be univariate normal distributions. So in a variational approach, we take the distribution that we have and we ignore the correlation. So the true posterior distribution has correlated parameters, and the mean field variational Bayes assumes independence. So instead of having the correlation taken into account, we just assume that they're independent and we optimize over that. So if you can change to the next slide, then if you change to slide, this one. So the example here, as you can see on the left, is the true posterior distribution So we sort of have a ridge, okay? And then we have the approximation is a independence between X and Y. So now it's a symmetric distribution, okay? And we're going to approximate from that. So if you go to slide 22, so this is much faster to do this, but it ignores the correlation structure. So the mean field variation approach assumes independence amongst the parameters. It may ignore important correlations, but we actually then, we can, it's much faster. So it's just to remember about this. So it improves accuracy at the cost of computational simplicity to do this. Okay, go to the next one. Slide 23. Okay, I want to talk about, what I want to do is just to see if I can share my screen, if you don't mind. Just stop sharing for a minute. Thank you. And I'm going to share my screen if I can. And I want to run through just an example of regression. So this is example of Bayesian machine learning. So can you see my screen?
Yes, we can see it.
Good. So this is the file examples Bayesian ML, which is you have as well. So this is an example of Bayesian machine learning. Now I've just set the working directory so that I can find my my files. You might put them somewhere else. Okay. So we're going to use the US crime data set that we saw yesterday. So we're going to just read in the data, so the crime data here, and I'm going to look at what those data have in them. And so down the bottom of my screen now, you can see we've got the different variables here. So we've got whether you're in a southern state, whether the person comes from a southern state, or sorry, the proportion, yes, southern state. So this is the region, I'm sorry. Education in the region, police in expenditure, and so on. So we have non-whites, we have wealth, inequity, the probability of going back to prison, the time here, and also crime. So crime is the number of crimes. So let's say we want to use, if we wanted to do regression, we've already seen an example of regression. All right, so I'm just getting ahead of myself a little bit here. But if we were going to use regression, remember yesterday, on day 2, we saw BRMS as a command, and we did some examples with BRMS. So if you want to do machine learning regression, you can use BRMS. And we saw an example from that from day 2. Okay, so I'll come back to this file as we go through, which has got some examples of the different methods that we're going to be using here. So if you can share your slides again, we'll just go to this first example of classification. Thank you. So we're going to go to Bayesian classification, and now we're going to talk about this as, so many of you have done this already. So this is going to look at how we can classify into the most probable class. So we might use this like logistic regression or probit regression, this kind of thing. So what we want to do is a supervised learning approach. So when we talk about this in terms of having a response and a explanatory variables, this is called supervised learning. The supervised bit is because we have a Y, a response variable. And if we don't have a response here, we have some Y's and some X's, and based on Bayes' theorem, we're going to classify the observations into different classes. And we're going to combine the prior knowledge and the observed data to estimate the class probabilities. So the probability of belonging to a certain class. The probability of a class given our data X is going to be the probability of the data given the class times the prior, and we get the most probable class, and we'll classify our observations into that most probable class. What we get from this is uncertainty estimates for our predictions. Now, there's other approaches, machine learning approaches for classification. We could look at other approaches which don't give us this uncertainty. But this is very useful for us to understand what's the probability that of belonging to a particular class. Thank you. Go to the next slide. And what we can see from this is just the next one, please. Hang on, just go back. Can you go back one more? No, sorry. Go back, back. 23, slide, okay, slide 24. Just go, yep, that's right. No, yep, that's it. Okay, so what we're going to do then is predict the most probable class. Okay, 25. I'm sorry to have to do this to you. Slide 25, okay. So what this now is a very, very common approach to classification, a machine learning classifier, is what's called a naive Bayes classifier. So this assumes independence of the predictors given the class. So now we can say, all right, I'm going to predict into a class and I'm going to use each of my predictors to help me predict into that class. And so the posterior, so the likelihood is going to be the probability of X given that class is going to be the probability of each of the X's for the different predictors given that class. And so we can just multiply up those probabilities. So if I have, for example, age and income, I'll say, what's the probability of belonging to a class given my age? What's the probability of belonging to a class given my, or probability of age given a particular class? What's the probability of income given a particular class? Now, what I want to know is what's the probability of the class given age and income? So I'm going to do that, that likelihood times the prior probability of belonging to a class, P of CK. So this is simple but very effective for high dimensional problems. For example, text classification, spam filtering. It's fast to train, it's scalable, and it performs well even with limited data. So the next slide. Okay, so this is an example of it. Let's say we have spam detection. So we have Y is going to be it's spam or not spam. So spam in Vietnamese is what? What's the word for spam? Can somebody tell me? Okay, all right. So you know when you, so if you have a bad email, for example, okay, unauthentic message. Yes, that's right. Thank you. Oh, let's just call it spam. Okay, thank you. All right, so we're talking spam. Good. Right, so we all know what spam is. So Y here is you could be spam or ham. Okay, so two things. And so we want to see X is going to be the number of word counts, which is going to be a high P. So it can be, so we have many different word counts. So we get the email, for example, and we're going to look at how many times different words appear in that email. And then we're going to try and differentiate by the sort of the number of times that words appear between what's a spam email and what's a good email, not spam. Okay. Now we have a prior probability on whether we have spam email or not spam email. And we also have a prior on each of the parameters. So this is for each word count, whether that word is actually going to be a spam or not spam. Okay, so we're going to have conditional independence given the class. So once I know that it's spam, then I've got one set of that's going to be independent, the relationship there versus if I've got not spam. So I can write down the model then, which is going to be a multinomial or Poisson for the counts. So the number of word counts that I have given that it's spam, or the number of word counts given that it's not spam. So I have a prior probability on it being spam or not spam, and I also have now a likelihood, which is this model that you see here. So I can put that together and come up with a posterior probability. So a posterior probability of whether this email is spam or not spam. So the Bayesian approach here puts priors on each of these word counts. And so we can say if we have rare words, so words that don't appear very often, then we don't worry so much about them because they're going to be, we can't really tell very much about them. So we put prior probabilities on those word counts about which ones we think are going to be most important. And we end up with posterior class probabilities. So for every email, we say, is it going to be spam or not spam? But we have some probability of it being spam. Okay. And that's very important because we might say, I'm interested in spam, instead of it being just anything over 50%, I'm going to class as spam, 50% probability. I might want to make it higher. I might want to say I'm only going to class it as spam if it's over 70% probability of being in that class. Or I might want to take a different approach and say I'm going to filter anything which has more than 40% probability of being spam, because I want to make sure I don't get any spam. Okay, or be very much more certain about it, not completely sure. Okay, all right, can you go to the next one? Here's another example. This is cancer diagnosis. So this is Bayesian logistic regression now. So for cancer, I have two types. I have a tumour, which is benign or malignant. So I have cancer, I don't have cancer, or I have cancer. And my X's here, my explanatory variables, are genes or imaging features. So many different genes to tell whether I have this, to be able to predict whether this tumour is cancerous or not cancerous. So benign means no cancer, malignant means it's cancer. So the model then is the probability of the tumour being malignant given all of these genes. Okay, and I'm going to fit that as a logit model. Okay, so a logistic regression. So I have two options now. I can do this using MCMC and estimate the betas using MCMC, or I can use variational Bayes, which is faster but more approximate. But what I'm going to do at the end is get a probability of belonging to each of the classes. And then I can make a classification, if I want to, based on a threshold. So if the probability of being malignant is greater than 0.5, I might say, yes, it's in malignant. And less than 0.5, no, it's not malignant. Okay? And again, I can change that probability. I can say the probability has to be greater than 0.8 before I'm going to operate on the person, do surgery, or the probability has to be greater than 0.3 and I'll do further tests. So having a probability of being in one class or the other class is much better than just having a yes or no, which is what we often get in just the regular machine learning methods. So the Bayesian approach gives us this probability of belonging to each class rather than just a yes or no. Okay, I'm going to now, can you go to the next slide? I think the next one's going to be, yeah. Okay, so I'm going to just ask you to stop sharing. I'm going to go back to the notes here. So I'm in the R file now. Can you see this? All right, so in this example now, I'm going to just, my little, I think I have this problem again. Let me try. It tells me that I can annotate, but I don't want to annotate. I could do this a minute ago, but I can't do it now. How frustrating. Do you mind sharing your screen again and then I'll just and then not share it and then I'll just try again? I'm sorry. Okay, and you can move now, yeah? Yeah, okay, all right. Can you just stop sharing and I'll just try now again? It tells me I can annotate, but I don't want to annotate.
Can you change to share full screen? Full screen.
Yeah, if I go to full screen, yeah, but I can't move. I don't know how to move. It doesn't move.
And you close it and open it again.
I could do it just a minute ago because I was showing you on the screen. Maybe I can just do this and show you bits of it. All right, so I'll just I'll show you if you can follow along in the from the notes. Just show you from the file.
Maybe you can share
sorry.
your entire screen. So when you click on the sharing button, then there are some options
maybe
like
that's probably better.
window or entire screen.
Screen.
Yeah, just give it a try.
Yeah, my entire screen might help. It doesn't allow me to share the entire screen, actually.
Okay.
I don't have a button to do that. All right, I'll share this much and then you'll go. So what you can see here is what I've done is taken as you saw before, we're going to use the crime data set. And I've just made a new variable here. So the line here is the US crime data set. And I've just made a variable called binomial here, binomial probability of incarceration. So I've said if the probability of incarceration, so the probability of going to prison, prob C, is greater than 0, I'm going to make it a 1. And if it's less than 0, I'm going to make it a 0. Okay, so that's going to make a factor, just a 0 or 1 variable for whether you'll go to prison or not. And then that's going to be my response. So this is going to look at, this analysis is going to look at the probability of going to prison based on this variable, given the other variables. So this is going to be education, proportion of non-whites, the wealth, inequity, that kind of thing. So I've created a training set and a test set. So we only have 47 observations in this, so they're the regions in this data set, so it's very small. And I've done that deliberately so that we can just see the results here. So I've got a crime.train data set, which is got 40 observations in it, and a crime.test, which has got 47. And I just check the numbers of successes and failures in the data set. So I've made a table for the number of successes and failures, or 0, yes and no, in the full data set, in the training data set, and in the test data set. Okay? And then I'm going to set up the formula. So this is the formula now. So I'm going to say the formula is going to be the thing that I've just created, the variable I've created. So this is the classification, 0 or 1, is going to be a function of, and I've just taken the first of these variables here. So whether you're a southern state, the education, police expenditure, et cetera, and you can see all the variables there. Now you can set a prior probability of a class. So you can, if you don't set the prior probability of a class, so this is in the package naive Bayes. So naive Bayes is an R package. The prior probability of the class will be just the observed proportion of observations in those classes, okay? But you can also set it. You could say it's 50-50 or 60-40 or whatever it is, and that can be based on the previous studies or on the knowledge about, what's the likelihood of going to prison for people in these regions. And so I've just shown an example there where you can set it yourself if you want to. And then you run the Bayesian analysis. You can run it without the specified priors or with the specified prior probabilities. And so it's very easy to run this analysis. You just go crime, you just give it a name. I've just called it crime.nb, so you can call it whatever you like. Naive Bayes is how you call the package. And then you say the formula, and I've created the formula up just above, so you can see where I've created the formula here on line 41. So I say that's the formula. I tell it the data set is going to be the training data set here, crime.train, created in line 32. Okay, and that's all I need to do. And there are lots of other variables that or parameters you can change, but the rest of it's just default parameters. Okay, or you can put in the prior probability if you want to, which is the second line there, line 47. Okay, and then you get a summary of the results. Does that make sense? Okay, I'm going to smooth this down a little bit. This is very frustrating. Anyway. Can you see my screen? Can you see my screen?
Yeah.
Okay. Oh, woohoo! Okay, good. All right. So if I run this analysis here, which I think I can do, you can see down here we get the that I've just run it down the bottom of the screen. You can move this up a little bit, and I can get a summary now of the crime.mb. So what this summary will tell me is that it's just going to tell me that I've just run the analysis, really, okay? And it tells me also what the prior probabilities are that I use here. So because I've just let it use the default prior probabilities, it's just given me it's used the proportion of yeses and nos in the data set. Okay, please tell me if you if this is not making, if you know if you have a question or a concern, because I can't see you so easily. Okay, so now what we want to do is we want to predict the classes for the test data set. So the command here is going to be predict for the data set, using the model that I've set up. So this is the results of the Bayesian analysis. So use the results of the Bayesian analysis here and fit the test data set. So we've split the data into a training set and a test set. We've done that because we keep the test data set, the analysis hasn't seen that data set, and we can see how well the analysis does at predicting the results of these new data that it hasn't seen. And I'm going to tell it to tell me about the class of them. So it's going to tell me whether that test data set, which only has 7 observations, is going to be in one class or another. So I'm going to run that line 51, and what it's going to tell me is that the results, so observation 41 is false, observation 43 is true. So these are the classes. So put the first of the test observations in class false. So this is like, will they be imprisoned? So it's a prediction of they're going to prison. No, yes, no, yes, no, etc. And if I want the posterior probabilities, not just a yes or a no, then I get that as well. So for each of these observations, I get a probability of being false and a probability of being true. So this first test observation here, a very, very strong chance of being false, 0.9997. The second one, very, very strong chance of being false. The third one, very strong chance of being true. The fourth one here is also very strong being false, etc. So you can see here that that these are the sort of results I get. Okay. Now I can also look at how well I am predicting. So this is the table of classes for the test data set. So I'm going to predict now for my modeled results here, and the test crime data set. So this is exactly what I have before, but I'm just going results now in this object, crime.pred. So we've seen that before. Now this one here is a table. So I'm going to table crime.pred. So it's going to tell me what the this is. So I've got false, false, true, false, true, false, false. Okay. Now I'm going to create what's called a confusion matrix. So this is going to compare the results from my prediction with the true values, so the observed data. So these are my predicted values and these are my observed values. And when I run that, I get this little table here. So down the bottom of my screen, can you see it? Can you see this at the bottom of the screen?
Yeah.
Okay, so this is saying here, if I predicted, this is the predicted crime here, I'm going to get false and true, and I've also got what I observed to be false and true. So I think these are the predictions, and these are the observed values, and these are the predicted values for false and true. So it tells me that I had 3 values that I observed to be false and predicted to be false, and I've got 2 values that I observed to be true and predicted to be true. And then I was wrong 2 times. Okay? So I can calculate then what's called the sensitivity and the specificity. So the sensitivity is the probability of saying it was true when it was really true. So if I calculate that, so the sensitivity is 0.5. So it's the probability of being true if it was really true. And you can see that's 2 out of 4 here, that I've predicted it to be true when it was really true. And the specificity is the probability of predicting it to be false when it's truly false. You can see here I've predicted 3 to be false when it's truly false, and I've got it wrong 0 times. So that probability should be 3 out of 3, and it should be 1. So let's have a look. And the specificity here is 1. So this is a way of telling me how good are my predictions based on this classification. This is a small example, but you can obviously scale it up. Now we can do some other things here. We can say, what role does education play in this prediction? So I get a table now that says for education in the false group, this is the mean and the variance for education. And in the true group, this is the mean and variance for education. So we can see that there's a big difference in the mean for the education parameter in the false group and in the true group. We can also plot that. So I'm going to do a plot to show you what that looks like. And what we get here is a posterior distribution for the education parameter in the true group versus the false group here. So we can see here that there's a very big difference between the true group and the false group there. Okay. So this is the next example in that R file, which I won't run, but I wanted to put it in here for you if you want to run it, is the spam data set from the notes. So this is a CSV file that contains 5,172 rows. Each row has each email, and there are 3,000 columns. The first column says the email ID. The last column has labels for the prediction. One is whether it's spam, true spam, or whether it's not. Okay, so that's whether it's, so we're going to use that as our response. So they've classified these 5,000 odd emails, and they've said they're either spam or they're not spam. And we're going to use this information to try and learn which of the word counts here, which of the words tell me whether it's spam or not spam. So these 3,000 columns are the 3,000 most common words in all of the emails. So we have each row email. We have 3,000 rows, which 3,000 variables, which are the common words in the emails and how often they've appeared. And then we've got whether that email is a spam or not spam. So if you want to, you can download the data set. It's a Kaggle data set here. It's a big data set, which is why I'm not showing it here, but you can do so. And then what I've done here is to show how you would write the code to analyze that using naive Bayes. So you're going to read in the data set here. You're going to then just I've made a response variable here. So this is spam.y is going to be my response variable. And remember, that's the last column. So that's going to be the ones and zeros. It was a spam or not a spam. So I'm going to then split the data into a training set and a test set. Typically, you can take 20% or 10% of your data as a test set and the rest as training set. And then I'm going to just check the numbers of successes and failures in the, or spam, not spam, in my full data set and in my training and test data sets. And then I'm going to write the formula. I write the formula for it. So I'm going to say spam is everything in the data set, all the 3,000 rows, and then run the Bayesian analysis. And so you can see here on line 109 and 109 is just the way that we run naive Bayes. Okay, so we just say naive Bayes, we tell it the formula that we've given, and then we give it the data. You can look in the package to see the other kinds of changes you can make, but I wanted to show you just how easy it is to run these sorts of Bayesian machine learning models using R. And then again, you can make the confusion matrix, see how good the prediction is, and you can plot some other things. Okay, is that helpful?
May I have a question, Professor?
Yes, please.
Yeah, we have two examples. The spam has a lot of observations, but the gram example, we just have only 47, and we divided it into two parts, test and train. So I wonder about the sample size for each of the test data and train data so that our result can be valid or something like that.
Exactly. So for this one, if it was me, I would be using all the data to do the analysis because it's too precious. You know, I've only got 47 observations, so use all of them in the analysis, and then you need to just declare that you've that you know you may be overfitting in the model. But that's okay, because in this case, in that example, I've split it into training and test to show you how to do that. But if you were analysing this data, I would recommend you use all 47 observations in the analysis. And the reason is that these are the regions in the US. And so it's not like you have other regions that you're going to predict out to. This is pretty much all of the regions. Does it make sense? So yes, it's a small data set, but I've used it because then it's easy to see. You can print out the data set, you can sort of see what you're doing with it. Whereas if you have the big spam data set, you know, you can't print it all out. So is that okay? Does that answer your question?
Yeah, thank you. But do we need any kind of limitation, like the lower limit for the sample size in general?
Yeah, so not necessarily. If you, so again, if you were writing this as an analysis, so you would just, because this is actually all of the regions, you can just analyze it for all of the regions. And the good thing about having the Bayesian approach is that you get probability distributions. And if you have a small sample size, then you will get wide credible intervals. So you can see then that you have a lot of uncertainty because you have a small sample size, okay? And so it's reflected in that. And then you say, these are my estimates, but I have a small sample size. The other thing too is if you have a small sample and but you have stronger priors, then if you can justify those priors, then you can actually support the analysis. And we've done that. For example, on day 2, I showed an example. We didn't go through it in big detail, but where I talked about having high-performing athletes. So there was this comparison between where the athlete trains, live high, train high, live high, train low, the kind of training that an athlete would do to see if they can win a gold medal. And so in that case, we've got a very small number of athletes who are at that level. We can't make more of them because there's only so many that are very good. So we only have a small number. So we then make that analysis more robust by using the priors.
Yeah, I see. Thank you. Thank you very much.
Thank you. Are there any other questions from people? Okay. How are we going? Shall we look at the decision trees? Are you happy to continue? All right, let's continue. Can you please share the screen again with the notes?
Please wait for a minute. I will try to share my screen because Miss Vern has gone.
Oh, okay, sure. Okay, thank you. All right. We want to look at Bayesian decision trees. So the motivation here is that we want to use a different kind of approach. Now, I talked a little bit about these approaches for decision trees in the lecture on the second day, where, or maybe it was yesterday, where we think about, instead of having a regression, so y equals beta naught plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 and so on. We're going to have a different kind of approach. And so we're going to take our data and we're going to split we're going to look at all combinations of the x's and the splits in the x's to try to separate out the response into two groups that are most different. So if I have a response that is binary, I want to have most of the ones on one side, most of the successes, and most of the failures on the other side. And so I find that the variable and the split that splits the data most, it's not going to be exact, but into the successes and the failures. If it's a continuous variable, I'm going to try to split it so that I have the biggest difference in the mean from one group and the other group. Okay, so now I've got the data, all of the data, and I've split it into two halves, or two parts, I should say. And so now I'm going to look at this part and I'm going to split it again. And I'm going to look at this part and I'm going to split it again. So what I end up with is all of the data together. I split it into two groups based on a variable and a split. And then I split those into two groups again. And then I split those into groups again. And I've run out of fingers now, but you keep doing the splits. And you do that until you reach some stopping criterion. For example, I have too small a number in each of the groups, or I have a good estimate in each of the groups. So then I will stop. And so I end up with this kind of tree. If you just stop sharing for a minute, I'm just going to bring up these extra notes. Hang on. Oops, that's the wrong one. I'm sorry, just let me see. Honestly, I give up. Let me try again. That was my fault, that one, because I had to. Okay. Let me see if this works. Can you see my screen? Okay.
Yes.
but I can't move again. All right, does somebody have these that they can just put up for me, please? Again, I can't move this screen. I'm sorry, can somebody just bring up that extra PowerPoint? It should be called Extra Slides, Tutorial for Extra Slides. Would somebody be able to bring this up?
Let me have you to share.
Thank you. Thank you. Okay, if you just go down to the next one. Next slide. Yep, keep going, one more. All right, so this is an example of this decision tree. So I've just given a very simple example here. So you might be hungry or not, and then the decision is going to be, is it midday? If you're hungry, yes, or hungry not. If you're not hungry, don't eat, okay? If you are hungry, you ask, is it midday? And if it's yes, you eat lunch. And if it's no, then is it after 6 p.m? In which case, yes, eat dinner. And if it's no, then have a snack. So it's a very simple example of this kind of decision tree. Now what we're going to do is to learn that from the data and have some probability of going to each of those different outcomes. So if you go to the next slide, the classification and regression tree approach we're going to consider all the possible values of all the variables in the data set, and we're going to select the variable or the value combination for a particular variable X that produces the biggest separation in the target. And that's going to be called the split. So we split the data, so we've got the biggest separation in the response that we're interested in. And then if any of the values is less than that threshold, then we go in one direction, go left, and then if it's greater than that threshold, then we put the data in the right branch. So we split the data into two groups, and we repeat the process on those two branches. And the result is a tree. So if you go to the next slide, here's an example of a tree. So this is a classification tree example for predicting the likelihood of a claim. So we have a commercial auto data set, 57,000 policies, and a 34% claim frequency. And the classification tree is going to look at how do we predict which of these, who is going to put in a claim. And so the first split here is going to be based on, so we have just the overall data, and then we split it based on the policies with more than or at least 5 vehicles. So they have a 58% claim frequency, and the other group has a 20% claim frequency. Okay, go to the next slide. Now we grow that tree. So instead of just having that, we now go to the group that has more than five or more claims, and we split that. And then we go to the group that has less than 5 claims, and we split that. And there can be different variables in the two different sides of the tree that we split on, and we keep doing that until we get to an outcome, to an end point. So if you go to the next slide, you can also see that in the tree then, it may not be the best way to model this data set, but in this particular node here, node 3 here, it's identified a specific node that is for policies with fewer than 5 vehicles. And fewer than 5 vehicles have a very low claim frequency in this data set. So this could be useful then as an underwriting rule or as an interaction term in a GLM. And so these are screenshots from if you go back just a couple of slides, I'm sorry, just keep going back one more, and the next one, and the next one. Right, so just forward one more. Just go forward. The next slide, yeah, stop. So this, in the previous one, yeah, these are the actual, I've got the link there to this example here. So this is from some lecture notes by Professor Chung, and you might want to, from CSU Ohio, and you might want to read this if you're interested in this particular example. So if you go forward now, please, and the next one, okay, this one. So the disadvantages and advantages of CART. So in many cases, CART, this classification tree, will not be as good. Just the single tree won't be as good as other methods like GLM. So it can't handle linear structure because it has to keep splitting the variables, and the data gets chopped thinner and thinner at each split. And we often need to prune it, which means take off the bottom layers, the bottom nodes, because they're just too noisy. And we just get one tree. But it's a very nice representation of the data. So you can easily see the splits in the data. And it's a good way to understand your data, to select variables and also search for interactions that you might put into a linear model. So I often use CART just to show what the data look like, and what variables I might want to think about in terms of interactions to put into a linear model. Now, this is building one tree. And so we might want to build multiple trees. If we're having problems with just one tree giving a good representation of the data, we can build many trees, but just make them shallower, so not as many groups. And if we think of many trees, then we have a forest. And so we think of this as being a random forest. Now, the way that a random forest is built is we take all of our observations. So we've got n observations in our rows of our data, and we have all of our columns. So we have p variables here, and I'm going to take a random sample of my observations and a random sample of my variables. So I've just got a smaller subset of data, and I build a CART model like we saw before, just with not too many layers, not too many splits. Then I take another sample of observations and sample of variables, and I build another CART. And then I take another sample of observations and sample of variables, and I build another CART. And you can see by this that I actually have like a random sample of observations and variables, and that gives me like a random tree. And then I build another random tree, so I end up with a random forest. And the advantage is that it mixes up the observations and the predictors, so it gives me a much better overall, a much better indication of the predictors for my data set. So if you can see here in the example, I've got the first tree, the second tree, the third tree, and the fourth tree will be built from different combinations of observations and predictors. And then I can take any observation and I can follow it through the tree. So the little blue dot is following an observation through the tree, and it will then end up in a final node, so the bottom node. and that will be, it will either be, in this case, a class A, B, C, or D. So if I follow that through, it's going to be in class C. In the second tree, it'll be in class D. In the third tree, that observation might be in class B. In the fourth tree, it'll be on class C. And so then I take at the end, I've got the observation was in different classes for the different trees, but I take the majority voting. So which class was that observation in most? And that becomes the final class. And you can see also I've got some probability of it being in those classes as well. So that's how we build a random forest. Can you go to the next slide, please? So the advantages of a random forest is that it can be used to solve both classification and regression problems. It's accurate and robust because it uses large numbers of decision trees to make predictions. It takes the average of all the predictions made by the decision trees, so that cancels out biases, and it doesn't suffer from this overfitting problem if we just build one tree. And it can handle missing values. So it can be used also for feature selection, so selecting the most important variables or features out of all of the available features from the training set. So go to the next slide. The disadvantages are that it can be a bit slower to run and it can be more difficult to interpret compared to a cart. So we're unable to include priors on the structure, the splits, and the important features. So what we can do is use a Bayesian approach, and a Bayesian random forest is called BART. So I'll just stop sharing that slide now, and we'll just go back to the other slides, if you don't mind. To the main slides. Do you mind sharing the main slides, please? The PDF. Thank you. I'm sorry to have to ask you to do this. I wish I could figure out what I was doing wrong. Right, so what we've seen is that traditional decision trees like CART are greedy, deterministic, and unstable. So these issues often limit the interpretability and the reliability, especially if we have noisy or small data sets. So next slide. So the Bayesian view treats the tree structure as a random variable, and then we have a prior over all of the tree structures, and then we update this prior with data. So, and we're going to learn then about the posterior distribution over the many trees. So the posterior samples capture the uncertainty in the splits and also the depth of the tree. And then we can average these predictions across the samples. So Bayesian decision trees address the instability by averaging over many plausible trees instead of relying on one, like the random forest. But now we also introduce into the random forest prior distributions. So a single tree can only represent stepwise, just a single split, and it's difficult to capture different kinds of relationships, and we have this problem of overfitting. So what we're going to do then is to use a Bayesian additive regression tree, so many different regression trees. We add them together, we put it in a Bayesian context, and that gives us a much richer decision tree approach for machine learning. Go to the next slide. So what we want to do is we're going to have this regression equation that we had before, y, an outcome, y, a response, and a lot of predictor variables, and we're going to approximate the relationship between that response variable and these predictor variables using this sum of these different regression trees that we're building. Each tree individually is called a weak tree because it doesn't have very good predictive power by itself. But when we combine all of the trees together, then we get very good predictive power. So it's an ensemble, a combination of small trees, and this is very flexible and it's non-parametric, and it has built-in regularization. So it's very stable in terms of the results that it gives us. Thank you. Next one. Right, so if you stop sharing for a minute, I'll see if I can share. I'll see what I can do. I have my little pointer back. Go away, pointer, I don't want you. Sometimes it shares and sometimes it doesn't, by the look of it. This is doing the annotation thing again, and I don't know why. All right, let me just do what I did before then. All right, I'm just going to show this part of it then, and you'll be able to see and run this yourself in your own time. All right. So on the screen here, you can see where I've run the, so I've just installed a package called BART. And so installed BART and the library. And then to run BART is just exactly the same as the kind of thing that we've seen before. So I'm going to use what's called WBART in the package. So WBART, and I give it the X's here, and I give it the Y here. I'm on line 146. And I then tell it the burn-in that I want, and I tell it the number of iterations that I want to keep, and then I tell it the number of trees that I want it to build. And then I run that. And then it will give me back a whole lot of information, so you can go names to see what's in this object that I've created, the results here. So then I can evaluate the MCMC chain here and see how good that MCMC chain is. And I can also do some predictions, so predict the results. So let me do that off screen for a minute, and then I'll come back to you in just a second and show you the results. Okay, so if I run the MCMC results, you can see this is what the MCMC draw is like for sigma. So what I've done is run the line that is line 150. So plot sigma here, and I can see the iterations for sigma. So you can do this for any of the variables then, the parameters, to see what you can see. So what I'm looking for here is any major pattern. I mean, if this was mine, I'd be looking to see why am I getting a big dip at sort of 5,000, 5,500 here. But generally, it's okay for sigma. Okay. So then the next part of the code says to predict the crimes using the BART model. So what I've done here for you is to say, well, let's predict using crime.BART for the last 7 examples here, 7 observations or 7 regions, and then I'm going to get the results. Now, BART output actually gives those to me. So it has a Y hat test mean. And so that gives you the predicted number of crimes in using that analysis. And then I can plot the observed versus the predicted values. So if I do that and I predict what I've observed versus what I've predicted, then I'll show you what I get here. So isn't this funny? Now it allows me to do this. I'm doing exactly the same thing, but before it was giving me that little annotation thing and sticking on the screen, and now it's fine. All right, so what I've done is I've plotted the observed versus predicted values here. I've also looked at the correlation between the observed and the predicted values, and I get a correlation of 0.97968. So you can see here, this is the observed data here on the x-axis, and the predicted data, predicted values on the y-axis, and this is for the 47 regions. So I'm doing pretty well for the ones where I've got lower crime values, and not so well for the ones with the higher crime. I've overestimated the underestimated the predicted values here. Right, so now I can determine which variables are the important predictors. So I'm going to compute how many times those variables appeared in the trees. Okay, so so let me do that much first. And when I do that, and then I get the results, what I see is this is telling me how important, how many times, what proportion of the trees these variables actually appeared. So how often did they appear in the trees? And that tells me how important they are. So you can see here that the important variable is really the proportion of like the spending, police spending in an area. Okay, so when I want to plot those variable importance, and I've just got an example of how to plot them here. So you can run that plotting exercise here, and what it tells you here is for each of the variables in the plot, you can see the variables that went into the model, and you can see the percentage of times that those variables actually appeared in the model. So that's how important they are. So you can see here whether it was a southern state or not is reasonably important, but not so important. The most important variable is the police spending. Education is also important, and also is the proportion of non-whites. So wealth and inequality has very little to do with this in this analysis. Okay, there's another package called BART machine as well. And so I've got some notes there about using BART machine. And if you'd like to run that, then you can as well on the crime data. So what I'm hoping from this is that you can see, you know, what the rationale is in these tree models, and you can also see how to run these sorts of tree models as well. Now we've used these BART models in practice in sport, so and in many other examples. So in the extra notes, I've got an example of in rowing where winning a medal is and predicting about winning a medal is often done not considering some of the environmental variables. And so we want to be able to add the understanding or the knowledge that the coaches have about winning whether the probability of winning. So if we just use the data, then we're not using the knowledge that the coaches have about the conditions of the race. And so we can incorporate that knowledge from the coaches into the model by using the priors and for the Bayesian additive regression tree model. So we get all of the advantages of the regression tree, the random forest, plus we also can add in this prior information from the coaches to then make better predictions. And so that's an example where it's really made a difference using these kinds of models. Okay. Thank you. Thank you for your patience in listening. Let's take a break for 5 minutes and then we'll just come back. So the time now is 10 o'clock. If we come back in 5 minutes, would that be enough time, do you think? Yeah, we'll come back at 10:05 and then we'll do the last part of the course. Okay? All right, see you then. Hello? Is anybody there?
Yeah.
Yes.
No? Can you see my screen?
Yeah, but can you make it bigger? You can download it onto your laptop, and then you can use offline software. Oh, it's great.
Can you see it now?
Yeah, but bigger than that,
Bigger?
more than that.
Oh, more, is it? Okay, hang on. Because if I make it bigger, I can't see it on my screen.
Okay, wait. It's
Hang on.
much better. Yeah. Thank you.
Okay, is that okay? You can see that now?
Yeah.
All right.
It's okay.
Let me just see. All right. Oh, now I've got the little dot back again there. Oh no, it was working.
You could put your mouse outside of the slide. Then it turned to the arrow again.
I'm sorry, what are you suggesting? Let me just try this again. I'm doing exactly the same thing, but when I do it one time, I get this into this box where I've got an annotation and I can't move. And then another time when I can get it so I can move. And I don't understand why I'm getting the two things. It's never happened to me before. So I'm sorry, but I'm going to have to ask somebody to share them again. I was so close.
Professor, do you have the file on your laptop? Because I think because you are opening your file as a top of your Google Chrome or something like that, so you cannot move. So I think you should open the file by using a software like Adobe Acrobat.
Yes, I do have it. I do have it open in. I see what you mean. Maybe that's true. Okay, maybe I'll try. Maybe you're right.
You can right click at the file and you choose open with, and you choose PDF reader like FOSIC.
Yes. Just bear with me for a minute. Okay. Let me go back to this and just see. I still have this. I don't know if you can see, I've got this little green dot. So which says that it's annotate. So if I then stop annotating, but then I can't move. So I'm sorry, just for now, can somebody else share them? I don't understand why. Sometimes it's giving me the little dot and sometimes it's not. So would you mind somebody just sharing the screen with me, please? Okay, all right. So I just want to talk about the last topic, which is a Bayesian neural network. So Bayesian neural network, then, can I see from people, can you just put in the chat if you've used a Bayesian network before? And what you've used it for. Has anybody used a Bayesian network? These are very common, probably the most common machine learning method. So, a neural network is like a regression model, but instead of having, what it's trying to do is to say we're going to have different connections between the different variables, and we're going to set it up so that it's like a network of connections, and we're going to have layers of connections between the different variables, and we're going to combine all of those together to give us a good prediction of the outcome. So the prediction of the outcome is going to depend on which variables we've connected, and then we're also going to look at how many layers that we have. So what's the depth of those connections? So we have a number of layers, and we also have a number of weights on the variables, and also and these different layers of depth. So the deeper the network, the more complex the relationships between the variables that we allow. And we also have different ways that we connect the variables together. So variables are typically represented through some sort of spline. So they have some relationship with the outcome of interest, and it's a non-linear relationship. So it's going to be like a little cubic relationship. So instead of just having a linear relationship between y and x1, we allow it to have a cubic relationship or a spline relationship, a non-linear relationship. So we have a non-linear relationship between y and x1. We also have a non-linear relationship between y and x2, but we also have a relationship between x1 and x2. So these models allow us to have relationships between each of the variables and also with the outcome. Now, the way that they're structured and created means that they can be very fast to run, but very flexible, but also because of that, then they can also they give very good predictions. So they are an excellent approach to prediction. So a neural network under a Bayesian paradigm says that the weights and the biases in the model, so the way that the model is structured, the parameters in the neural network are treated as random variables. And so the goal is to learn a posterior distribution over all of those different parameters in the model. So that's the relationship between each of the x's and the y's, and then the relationship between the y's themselves at these different layers, so the layers of complexity in the model. And so we're going to then learn a posterior distribution over each of those relationships as opposed to just a single estimate. So again, we have this formulation where we have the posterior distribution for these parameters in our neural network, given the data, is going to depend on the structure of the neural network and the data that we have available times the prior that we put over each of these different parameters. So each sample of theta then represents one possible model, and then we average the predictions across the samples, and that captures the model uncertainty. So a Bayesian neural network then allows us to incorporate model uncertainty. So we get that from limited or imperfect data. And it also quantifies that posterior distribution for all of those weights of the different variables and the way that they connect to the observations. This kind of model uncertainty decreases as we see more data. So as we get more data, we get a stronger estimate of the model. And the uncertainty will be higher when we have inputs that are like out of distribution. In other words, if we have outliers or we have other inputs that the model hasn't seen before. So these kinds of inputs then give us greater model uncertainty. And that's what we want. We want to be able to reflect those differences in the inputs through the uncertainty in the outputs. We also have data uncertainty. So the model will incorporate, a Bayesian model will incorporate the uncertainty in the data. So that we know that our data comes with inherent variability or noise, and we capture that usually through the likelihood. So again, we can write down the likelihood, but even if we have more data, we still have, variability in those data themselves. So there's some variability in the data that we capture, but doesn't decrease because we just get more data. What does decrease is we use all of that data to give us better estimates of the theta. So we have model uncertainty and we have data uncertainty. And a Bayesian neural network quantifies both of those. So when we do predictions from a Bayesian network, we get estimates that incorporate both the model uncertainty and the data uncertainty. You go to the next slide. So we can use Bayesian neural networks to get better predictions. When we fit, as I said, the number of layers in a network will increase in the complexity and give us better predictions. But just like when we talked about for the decision trees, if we have too many layers, then we overfit the data. And what I mean by that is that we get very good predictions for our data, but then it's not very good for predicting outside. The other thing is we get very good predictions and we think we have very good predictions. So we're overconfident in those predictions. But in fact, we could be wrong. And so we want to be able to have more uncertainty in our model and represent that uncertainty both from the data, coming from the data and from the models. So standard deep nets can overfit and give us overconfident predictions. And this is really critical in examples like autonomous driving, self-driving cars. Underpinning a self-driving car is, as we talked about yesterday, a Bayesian network or a Bayesian neural network, or just a neural network. If we just have a neural network, then we can get overconfidence in our estimates. So a neural network could be learning to drive the car, and if we have a Bayesian neural network, we might put in other information about how drivers actually behave. And so if you're thinking you're driving a motorbike here, riding a motorbike in Ho Chi Minh City, and there are different ways, different rules that you would follow that may not be the written rule, like the autonomous driver might drive by the law, but it needs to be learning from the way that people are driving as well. So there are rules that it needs to learn, and the Bayesian network is a very good way of learning these approaches. Again, because like we talked about in the first day, we have this updating of information. As we get more data, then we update the model and the predictions. So a neural network will have a model and it gets new data and it updates that model. So if you're thinking about it as a self-driving car, it starts out and the neural network will only learn from the law, okay, or the way, the way that you should drive. But as it's driving, it gets more information about how people are driving and it updates its estimates of how to drive. And so as it's driving, it learns from the other drivers about how to drive in that traffic. And so that's an example of having a model, getting some more data, updating the model, getting some more data, updating the model again. So your current state becomes your prior, you get some data, you update the estimates of the model, so then you can predict better. So the self-learning car or self-driving car will learn to predict how to drive better as it gets more information. But it can't get too good. It can't be too confident because it needs to have some uncertainty in case something different happens. You know, as a driver or as a rider of a bike that you drive, your regular way, but sometimes different things happen. A car pulls out, or another driver cuts across you, or somebody steps out from the road, or your bike gets a flat tire. These things that you need to, that the self-driving car may be overconfident in how it behaves, and it has to have, it must take into account both the uncertainty in the data and in the model. So this is also important in finance. So we can't overfit or give overconfident predictions in finance, for example. So the Bayesian approach then gives us better calibrated predictive probabilities through the posterior predictive distribution, which we saw on day one. It gives a natural regularization through the priors. So you put in other information in the priors, and that helps it to be not so confident and less overfitting. And it distinguishes between the different types of uncertainty, the model-based uncertainty and the data uncertainty. It's data efficient. It can learn from small data sets because it has priors, and it provides a good theoretical grounding for ensemble methods, so combining different neural networks, or combining a neural network and a decision tree kind of thing. So Bayesian neural networks really combine deep learning flexibility and the Bayesian uncertainty quantification. So can you go to the next slide? Right. So this lecture has talked about Bayesian machine learning. So the way that we learn from the data by updating priors with evidence to form posteriors. We also see inference, so MCMC or sampling-based approaches versus variational Bayes approaches. And the models that we've covered are Bayesian classification and naive Bayes, Bayesian decision trees, BART, and Bayesian neural networks. So these Bayesian methods unify the way that we do inference, we do prediction and uncertainty across simple and complex models. Okay, that's the end of the lecture. So if you go to the next slide, we'll just spend a little bit of time on the tutorial. Here are some references for BART, and there's also some references in the extra slides and also in the R code that I gave you as well. So thank you. If you can go to the next slide. So we'll just go to the tutorial now, and I'll just spend a short time, so it won't take us an hour to get through this, but we'll spend a short time just talking about some how to implement this. So you've seen the code. I've given you some code, so you can run that if you run it in R. But I'll just talk through some of this very in a general level as well, in case you don't want to go into the code. So the software for naive Bayes is naive Bayes package. So you just search for naive Bayes, and what we need to do is we need to prepare the data. So we need a response variable that's going to be categorical, categories or binaries, so two groups, and a predictor matrix. So that's our X's, and they can be continuous or discrete or mixed. And we split the data typically into a training set and a test set. And we're going to then choose our conditional distributions. So we can just run, as you saw in the code, naive Bayes, and that's fine. Or if you want to, there are specialized distributions you can have. So you can have continuous features, Gaussian naive Bayes, you can have multinomial naive Bayes, or you can have Bernoulli naive Bayes. So in your own time, then you can look through these options if you want to be more specific about the type of naive Bayes approach you fit. So if you go to the next slide. So we fit the model, and you saw an example of this in the R code. We take model, whatever you want to call it, dog or crime.nb, which is what I call the crime example.naive Bayes. So whatever you want to call it. And then you call the naive Bayes package, so naive Bayes, and then you say y is a function of, so y tilde and have your x's. If you just put y tilde dot, it means use all of the other variables in your data set to predict y. Now, in the code that I gave you, I changed to that to have a formula line that I had created outside that. And then I put the name of that formula into this command. So then it means that I can change the formula anyway, and then it will run the same code. So you can choose whether to put the formula inside the code, inside here, or make a separate formula line and then put that name of that formula into the code here. Okay. So then you tell it the data, and you tell it, you can use this command, use Poisson equals true if you wish. So it's just a way of displaying the results. So in my code, I didn't use that. Here, you can see there's an option to use this. So it gives you a different, it gives you, if you're using like the word count example, the spam data set example, then it will display the number of items that will be in each of the groups as well. So then you can predict new observations by using the predict command, and there's an example of that in the R code, and you will get posterior class probabilities, so the probability of belonging to one class or the other. We saw an example of that earlier today. And so then you can interpret the result. You can inspect the class probabilities, and you can also plot the conditional densities or the likelihood tables. And there's an examples of that in the code as well. Okay. So this is the example here of specifying like the spam data set. So I've talked about. So this is in like what's actually happening when we run that data. So we classify emails as spam or not spam using the 3,000 common words and how many times those words have appeared in each email. So each email is a row, okay, and then each column, the 3,000 columns, is a word. So it might be thrilled or under or pay. You know, if you might have pay immediately, something like that. So you're looking at these words and how often they appear in the email. And sometimes it's only one. It could be a 1 or a 0. But if you have many emails, then you're going to tell how many times those words appear. So if you get a spam that says pay immediately, no, otherwise you will be, your account will be closed, for example. That's a spam email. So it has words pay, immediately, account, closed. Okay, so you would have a 1 for each of those words. And if that appears often in spam emails, then that will pick out whether that that email is likely to be a spam. So we're going to classify the emails as spam or not, depending on how often these words appear. So we're going to have a predictor matrix, which is these counts or frequencies of the selected words, and our response is whether it's spam or not spam. And the workflow then is to specify prior class probabilities. That can be done just by default. The package will pick will select the proportion in the data set, the proportion in each of the classes, or you can specify it. You can then, we have a model for the word likelihoods. So the probability of that word appearing if it's a spam email and the probability of the word appearing if it's not a spam email. That's not what I want. I want what's the probability of it being a spam email given that those words have appeared. So it's again this reverse probability that we looked at in the first lecture. So in the first lecture, we looked at what is the probability of a disease, of screening if you've got the disease, successful screening if you've got the disease. What we want to know is if we get the screening, positive screening, what's the chance of us having the disease? So it's the opposite, okay? So what we have the same thing here. We've got, now we know for the spam emails, what's the probability of the words being in that spam email? What I want is, given that I've got this email with these words in it, what's the probability that it's spam? So it's this reverse probability that we can do through Bayes' theorem. So we now want to calculate then the probability of it being spam given that I've got the words. So P of Y equals K given X. And that's going to be proportional to the probability of having those words given that it's spam times the probability that it's spam. And so then I predict the class with the highest posterior probabilities. So for that email, there'll be some probability when I calculate the posterior distribution. There'll be some probability of it being spam, some probability of it not being spam. And I'll choose the class with the highest probability. So I can implement this in an R package in naive Bayes that you've already seen, okay? All right, next. Now, when I want to do BART, as you've seen before, we can use a number of packages. In the R code, I've shown you to use BART and also BART machine, okay? There's also another package, Bayes tree, which will fit these as well. So you can fit BART for regression or classification. You can do that in any of the three packages, Bayes tree, BART, or BART machine. They have slight differences in terms of the type of output, the visualizations, and that, but basically they give the same estimates. So what we're going to do in BART is we fit the model using many different trees, and then we combine the trees. Okay, so that's what the model is here. So it's going to be this sum over all of the trees, which are represented by G of X here. So we prepare the input matrices, X dot train and Y dot train. That's going to be the training data for X's and the training data for Y. And then we run BART. We tell it what's the explanatory variables, X, or the predictor variables, X, in my training set. What's the Y, my training set? I tell it the number of trees, and I tell it how many iterations I want to save, I want to run it for. And so the function then samples the posterior trees via MCMC and returns the posterior mean and credible intervals. And it also tells you the variable importance and the partial dependence plots. So it's how each of the X's are related to the Y. So you then can compare posterior predictions to classical regression or decision trees if you want, but you also get the uncertainty in in these estimates reflects the variability across these different trees. So again, like all of the approaches we've seen, we're taking an approach where we're looking directly at the probability that we care of the parameters we care about or the outcomes we care about, given the data. We're incorporating uncertainty into that, and then we're allowing us to be able to come up with better estimates that reflect the true uncertainty of the parameters. Go to the next slide. So the software that we can use for Bayesian neural networks is Bayes Flux. So I haven't given an example of this, but if you're interested in Bayesian neural networks, you can use Bayes Flux, and this provides a modular framework for defining, training, and analysing Bayesian neural networks in R. So we take the parameters of the Bayesian network, which are called the weights and the biases in these different layers and the connections between the variables and with the response. And those are treated as random variables, and we put priors on that. So the model learns their posterior distribution via an MCMC algorithm. Go to the next slide. So again, we define the model architecture. So we use network module. So that'll tell us the number of layers and the way that the neural network is constructed. We specify the likelihood and the prior modules, and then we train it. So we train it using an MCMC sampler then to sample from the posterior distribution, and then we analyse the results. So we look at the posterior samples and we get estimates of these neural network parameters. So it combines the deep learning flexibility with the Bayesian uncertainty quantification. We get full posterior inference rather than point estimates, and we can use GPU acceleration, so we can use like TensorFlow, so we can do fast computation. Now, Bayesian neural networks, because we're using MCMC, or even if we use variational Bayes, will take longer to run than regular neural networks. So like non-Bayesian neural networks can take a while to run, but they're relatively fast. If you use Bayesian neural networks, it will be much slower, but you get more information for it. So you have to choose for neural networks, I think now, you choose whether that extra information is what you need or what you want. So in practice, if you haven't used neural networks before, or even if you have, try running the sort of the regular neural networks before going to a Bayesian neural network. When you're familiar with running a neural network, then try a Bayesian neural network. That's my advice. Next slide. So a case study here is to predict cancer malignancy using patient imaging or gene features. So we have continuous clinical or imaging features, and the outcome is to predict whether the tumour is benign or malignant. So we define the network's architecture using network module command. Then we assign priors to the weights and the biases, and then we train it to sample from the posterior distribution, and then we compute that posterior predictive distribution, which is going to predict for our test data whether it's the tumour is benign or malignant given the X's. So we get a posterior mean, which is a point prediction, but we also get a posterior spread, so a credible interval around that prediction, the predictive probability. So we can use Bayes flux to do that. Okay, next slide. All right, so there's some extra references there for the packages, and as I said, there's extra references in the other material as well. So just go to the next slide. Okay, so what we've done in this tutorial is review the software tools and also looked at some case studies for classification and for Bayesian neural networks. Okay. So if you just go out of your slides for a minute, I'm just going to bring up the, hopefully, okay. All right, so that brings us then. Are there any questions about those the lectures for today and the tutorial? Yes, please.
Yeah, may I have question about the name? Because yesterday we learned about Bayesian network, and today Bayesian neural network. So I'm wondering, they are the same or different things?
No, they're different. So so there's still network models. So there's still different ways. Like the first day we also learned about a graphical model. So they're all and so then the Bayesian network, you can think of the one that yesterday when we talked about it, it's a form of graphical modeling. This one too, and it's just a different type of network. So if you think about like a regression model, we have y equals and then a linear combination of the x's. So x1, beta 0 plus beta 1 times x1 plus beta 2 times x2, so a very linear relationship. We think about the decision trees as saying, okay, I've got a y, a response, and I'm going to split the data up into the different components. And then I can, that's a CART, a classification and regression tree, and into different subgroups and other subgroups. And then I can build a better predictor by having multiple decision trees, and that's the random forest approach. And then I say maybe the data's just not split into different groups like that. Maybe I can think about it instead, not the regression model or the tree model, but I'm going to think about the outcome and which variables are important and which variables are important into those variables. And I build a much more complex representation of the way that the x's predict the y, okay? And in a neural network is a different way of making that representation. So now I'm going to have a different way of combining the x's, not through that sort of the directed acyclic graphical structure, but a much more flexible structure between the x's and the y. And then that's where we get the neural network. So it's just the degree of complexity and structure in how I relate the Y to the X. So the Bayesian network structure and the neural network structure, even though they have the word network in them because they're connecting the X's together with the Y, they're the same sort of idea of creating a network, but they're a different kind of structure. Does that make sense?
Yeah. So the neural network, how to structure the relationship between between Y and X? You also based on the literature review and some kind of experts part of it, right?
Well, the structure for a Bayesian network will be learned from the data. So yesterday when we looked at a Bayesian network, not a neural network, just a network, so yesterday we created that structure ourselves. Yeah, we said, okay, well, how will we create this model? Much the same as when we do a linear regression. We say, we create that structure. We say x1 plus x2 plus x3, maybe an interaction between x1 and x2. We create that structure. In the Bayesian network, we also created that structure yesterday. You can use a software like BNLearn and learn the structure of that network, okay, if you've got data. So if you've got a lot of data, then you can learn the structure of a Bayesian network, which will still have that kind of directed result. So, the outcome, factors that affect that outcome, factors that affect that outcome, and so on. So, for example, in genetic analysis, you might have a lot of genes and you learn the structure between those genes. And that can be quite complex, that network structure. So that can still be a Bayesian network that you're learning, okay? A Bayesian neural network will, again, you learn that from the data. So you don't make that structure yourself. You learn that from the data, but what you can do is put on priors about the parameters when you learn that from the data. Does that make sense? Yeah. So you don't set up a structure for a Bayesian neural network yourself, but you can say, all right, well, I know that it's going to have connections between the X's and the Y's, and I know that it's going to have connections between the X's, and so that's when I can put on the priors on those terms. I'm just not quite sure how that will be, how many, and I can also set the number of layers actually. But at the end of the day, I'm not going to know until the analysis is done what the data tells me about those actual connections. Any other questions?
May I ask something about the batch model? You find that
Yes.
the fx is the sum of the regression tree. So
Yes.
how we define the trees, each tree? Yes.
Yeah. So each tree is like a cart tree. So again, it's going to have just the same sort of splits. So remember, it's going to take the data, take a random sample of the data, and then split that data into a random sample of the data, a random sample of the variables, and then it splits that subset of the data that you've collected, that you've sampled, and then it will split that into two groups that are most different, and then take one of the groups and split it again, take the other group and split it again. The variable that it splits on and the value that it splits. So it might be splitting on age, and it takes people less than 30 or greater than 30. So it's chosen the variable age, and it's chosen the split to be at less than 30 or greater than 30. And it's done that because age was the best variable to split the data, and the age at 30 actually gave me the best separation between my response variable for those two groups, people less than 30, greater than 30. Then I'd take the people who are less than 30 and I would split maybe on education, if that was the next way of being able to generate a separation between in the data. for the response. So I do that, and I just build them quite short. They don't have to be very good predictors by themselves, but I build many of them, and then I have the sum of those, and then that gives me a good prediction.
I see. So how about the value of m? Because this is the sum from the J to m, the number of the tree, the m.
The number of trees?
Yes, the number of trees. So
how many do you choose?
Yes.
Yeah. So so that can depend on a couple of things. So if it depends on the sample, the size of your data. So if you have a lot of data, then you can build a lot of trees. If I have a smaller amount of data, like for example, in the data set, the crime data set, there's 47 observations or 47 regions, 47 rows. So I can't do many there's still many random samples I can do, choosing different combinations or different subsamples of the rows. But after a while, I'm not going to learn anything new by doing more samples. So doing, say, 20 trees for that data set would be enough. If I have a much larger data set, for example, the spam data set, I might want to do 200 trees, because I'm going to, when I take a sample of the observations and a sample of the predictors, I'm going to, I might see something very different from that, different combinations of the predictors and of the observations, the emails in this case. So some of that is a judgment, but you do many trees. Now you don't want to do so many that you get over prediction. But typically, you can do, say, 200 trees, and that would be a good number, unless you've got a very small data set.
Thank you.
Any other questions? Does anybody want to put a question in the chat? No? All right. Well, that brings us to the end of the course. And I'm just going to bring up this slide to acknowledge then everybody. So I want to acknowledge Katie Dang and Kane for helping to develop the course. I also want to acknowledge Nyok Tran and also the ISI. In particular, I'd like to acknowledge you for being such great course participants in the course. And thank you very much to the organisers of the course as well. Local organisers, you've been fantastic hosts here, and I've really enjoyed being able to share this knowledge with you. And I hope that you found it somewhat useful. And I wish you all the best in your research and your work going forward. Thank you.
Hello.
Hello.
I'm here. Yeah. I sent message to Vice and Professor Trần Minh Ngọc to join the ending of first class in Ho Chi Minh City, but I'm not sure whether they can join. Please wait a moment. I check with them. Okay, Minh Ngọc will join us in a few minutes. So thank you a lot, Professor Carey. Minh Ngọc have something I would like to say with you. Okay. Okay, I'm sorry about the weather forecast. They tell us there will be some storm in the central parts of Vietnam and may affect to the south part in Ho Chi Minh City. for safety of all students, my university make an announcement that all students have to study online today. So here now in university, no student, just a few students they still come because today it's not raining, but no one here. So I'm sorry we have to change the section into online. But I think everything worked through. Wait a minute for Minh Ngọc. He joining us. Minh Ngọc, where are you? Are you here? Okay. So, yeah, I'm happy to see many of you stay online with us for the last section. And many like smile on the screen. Minh Ngọc. Hello, Minh Ngọc.
Hi, Tonang. Hi, Carrie.
Hi, Minh Ngọc.
So I would like to introduce to all the participants as Professor Minh Ngọc, who I mentioned at the opening ceremony that he made the connection between ISI and me at the conference in Taiwan last year. So through the connection, he helped us to establish the ISI lecture in Vietnam. And I also mentioned that that's just the start, and we will have more program to develop statistic background in Vietnam. So Minh Ngọc, I would like to invite you to say something with us. And I also see here Mr. Trung Giang from Vinh University, isn't it? Hello.
Hello, chị Tuấn Anh. Hello, anh Minh Ngọc. Hello, Carrie. This is Giang. I'm from Academy of Finance, Hanoi.
Right. Okay.
Yeah, Minh Ngọc, please. Sorry.
So thank you, Tonang. I just popped in to say hi to everyone because I have meeting just in a few minutes. But Carrie, I hope that you have enjoyed so stay so far. The weather has not been very nice in the last few days, but I hope that is okay.
It's been lovely, thank you. It's great hospitality. I've been very well looked after, and I've really enjoyed meeting the students and the participants in the class. So it's been very good.
So I trust that Tonang treat you well, right?
Very much.
And to the participants, I hope that I trust that you have enjoyed the class. You have learned a lot from Professor Carrie Mangus in the last few days, and keep in touch, because to me, I think that this is not just about the class, but about the connection and about the future collaboration between not just you, but the Vietnam and Australia in the future. So keep in touch. So Carrie, so Giang here will be from Hanoi, and he will take care of you when you are in. I know Giang from Hanoi, right?
Thank you.
And, did you book the train to? I know to Hanoi. So when are you going to Vinh?
To Vinh on Sunday.
On Sunday, and by that time, I think that the weather should be okay.
I hope so. Yes.
Yeah, I hope so. Yeah. So I have to go now because of the meeting now.
Sure.
So
thank you, Minh Ngọc, for joining, and thank you for organising this. It's been very good.
Yeah. Okay, I have to go now. So bye bye, everyone.
All right. Bye.
Carrie.
Yes.
Yeah, I'm hosting you in Hanoi, but the work email, you set it in living mode, so I cannot get in touch with you on the email, via email. So how can I reach you?
I don't know. Can you I'll check my email then. Maybe something's wrong with it. But yes, my email is the best way. So I'll get in touch with you just after this. I think you've been in touch with Chantel. Yeah.
Yeah. I have some questions to gain the idea about where you want to stay you want to stay.
Okay, all right. Perhaps we can we stay on the call after we close this session then? Would you mind staying on?
Yeah. So I gonna send you another email, and hopefully it can reach you. Otherwise,
if you can just stay on for a little while, then we can talk just after we let all the participants go, maybe.
Yeah, I would like also to say something before we close, and then you and Professor Carey can discuss detail later after the class leave. Okay, so Carey, would you like to say something? I also have something to say.
No, I just wanted to say thank you very much for all the organisation and the great hospitality. It's been excellent. So thank you, and thank you to all the participants for staying till day 4.
Okay, and I'd like to say, dear Professor Carey and dear colleagues and dear participants, on behalf of the University of Economic Ho Chi Minh City and the College of Economic Law and Government, I would like to say thank you again for Professor Carey for your inspiring lectures during the course, and you have brought us a great knowledge, enthusiasm, and encouragement on of us. And I would like to say thank you to International Statistical Institute and the VISM, Vietnam Institute for Advanced Study in Mathematics, again, for GFG office team and all the participants for your participation and your enthusiasm during the course. And I see the number of attendants here. It maybe approximate the number at the beginning, so no one drop out of the course. That's it. I'm happy for the organizer and for the lectures. Before closing, I would like to announce to the participant that the certificate will deliver by email to participants who attend at least half of the sections, but we send later after the course. And once again, thank you very much, and we look forward to meeting you again in a future activity at UEX. And I hope that Professor Carey, we will keep in touch, and maybe we will have more activity and collaboration in the future. And I hope that we can have a dinner before you leave Ho Chi Minh City, maybe on Saturday night. Okay, and I'll send you an email later. Okay, thank you all participants. Do you have something to say to Professor Carey? Someone, I dream on many participants here. Yeah, I dream and Thục Anh. I dream you first. Please turn on your micro. Turn on your micro, please.
Can you hear me?
Yeah.
Yes, yeah, please.
So I want to say thank you, Professor, and everyone here. I too love this course because I learned a lot from you, the way you control the class and the way you give us embracing in everyone. Yeah. So I hope to see you again in one day, and thank you so much.
Thank you, Ajahn.
Yes.
Thank you.
And Thục Anh, please. Thục Anh, you would like to say something? Yes. Thank you.
Yeah, I can open the camera since there has been a technical error. Anyways, I feel very grateful for UEH department to offer me the chance to listen to an in-depth section lectured by Miss Carey Morgensen about statistics, about Bayesian statistics. And I want to, thanks to her materials, I can get more in-depth research for my own, and hopefully I can build up my portfolio and pursue this career path in the long run. And not that I was a K46 alumni at UEH ISB, and that is my great honor to come back. To listen, and thank you. Yeah, I feel extremely grateful. Yeah.
Yes, thank you.
Thank you very much for those comments.
Okay. Okay, and then thank you. There's so many thank you message on the chat. Okay.
Okay, thank you very much, everybody.
Yeah, we can have a offline picture again, but not not now. Okay, so bye bye everyone. And I will send you an email, Carrie, later. Okay, and now you
Okay, thank you.
and Mr. Trường Giang can discuss some detail for the preparation in Hanoi.
Okay, all right.
Okay.
Thank you. All right. Bye.
Yes, bye. Giang cứ trường thảo luận với cô đi nha, mình nói văn phòng để link lại.
Okay, thank you, chị Tuấn Anh. Yeah.
Okay. Bye. See you later, Carrie.
Yes.
Bye. See you. Thank you very much again.
Yeah.
Goodbye. See you later.
See you, man. Thank you.
Hello, Carrie.
Hello. Yes, I'm sorry to. Yep.
Yeah, I was in the lecture in the last hour. Yeah, I like the way you teach. Yeah, it is